Hi, and welcome to the videos for section 3.7 for Math 126. This is the first of 5 videos. Yep, you heard me right, 5. It's a long section. It's a very important section. We're going to go through a lot of information that you're going to have to apply on in-class exams, final exams. So section 3.7 has to do with rational functions. And so, first video we had, we talked about what? Rational numbers. We had what? Rational equations. Now we have rational functions. And every time we're dealing with rational, we always are dealing with what? A ratio or a fraction. And that's what we have here. So a definition is that a rational function is of the form Rx, our rational function, is some polynomial p of x divided by a quotient polynomial, so we call it q of x. It's basically one function in the numerator, one function in the denominator, a polynomial. We also have the domain consists of all real numbers except those for which the denominator is 0. And so the thing we need to be concerned with, so when we were talking about domains before, it was always what? Do we have a radical? Do we have a denominator? Because we're dealing with polynomials, we don't have a radical in the numerator. So our biggest concern is what value of the polynomial in the denominator is going to make that rational function undefined. And so one thing that we have to be careful now is that we must pay special attention to the behavior of the graph near those x values. So, when we were graphing polynomials, just polynomials, not rational functions, what's the first thing we did? We figured out what's the end behavior. Well, in this case, because we have a fraction, our concern is what makes the denominator 0, what values, and then also, as the graph gets close to those values, what happens? Is it going to positive infinity? Is it going to negative infinity? So let's look at an example. We want to graph f of x is equal to 1 over x and state the domain and range, actually. State domain and range. So this is the most basic of our rational functions. 1 in the numerator, x to the first power in the denominator. This is as basic as it gets. So the first thing we want to know is, where is the denominator equal to 0? That's because otherwise any other value is fine except for that value. Well, because it's just x, that means that it's not defined or undefined at x is equal to 0. So if I start plotting what this graph is going to look like, So I can't have x equals 0, so I don't have any point on the y-axis. What about if x is equal to positive 1? Well, if x is positive 1, so let me make a little table here. So for my positive values of x, when x is 1, the whole function is what? 1 over 1, which is 1. So I have a point here. As x gets really big, so x is 100, x is 1,000, x is 1,000,000, well, what happens? 1 over 1,000,000 is a super small number. So the bigger that x gets, so if we say as x goes to positive infinity, my function goes to what? My function goes to 0. 1 over 100, small number. 1 over 1,000, smaller number. 1 over 1,000,000, smaller number. So it's never going to hit 0, but it's getting very, very small. So basically this thing flattens out as I head towards positive infinity. Well, as I pointed out here, we have to pay attention to what happens to this graph near the values where it's undefined. So as x gets closer to 0, what happens to this graph? So if x was, let's say, 1/10, so it's smaller than 1, but not quite 0. So as x is 1/10, what do I get? I get f of x is 1 over 1/10, which if I keep change flip, is 1 times 10 over 1, which is 10. So at 1/10, I'm all the way up at 10. Well, what happens when it's 1/100th? Well, now that value is 100. What about when it's 1 over 1,000,000th? It's still greater than 0, but it's almost at 0. That thing's going all the way up to positive infinity. So when my x values are positive, I get this sort of, I don't know, what is that? Like a cup shape a little bit, or an L shape maybe. I get this L shape that goes through 1, 1, but it never really hits 0. And so as x gets close to 0 from the positive side, it's going to positive infinity. Now, let's look at my negative values. If x is equal to -1, well, if I plug in -1, so x is -1, plug in -1, I get 1 over -1 is -1. So that means I've now jumped to the opposite side of the graph. But the end behavior, and the behavior as I get close to 0, still mimics what I had here. If I have x going to negative infinity, so if I have 1 over -100, it's a really small negative number. If I have 1 over -1,000,000, it's almost 0, but it's on the negative side. So this one is going to be getting closer and closer to 0 as I get towards negative infinity. And then similarly, between -1 and 0, if I have -1/10, then my f of x is 1 over -1/10, which is 1 times -10 over 1, which is -10. So that's really far down, and this one is going to head towards negative infinity as I get close to 0. So this function, so that's the graph of this function. Two things I'm going to add in here. So this function will never hit 0 on the y-axis, and the function can never be 0 along the x-axis. So I can't pick any value for x that's going to make the whole function equal to 0. So these are what we call asymptotes, and we identify it with a dashed line, in this case on both axes, which when I look at this graph says this function will never hit those values where the red dotted line is. Otherwise, that's what the graph looks like, the sort of L and then the, I don't know what that shape would be, an upside down L. So, as I said, these red lines are what's called asymptotes. So in this particular case, the line x equals 0, which means what? X is 0, that's my y-axis. So the line x equals 0 is called the vertical asymptote. And the line y equals 0. So when y equals 0, that's what? That's my x-axis, and it's horizontal, so as you can imagine, the line y equals 0 is called the horizontal asymptote. And so this vertical asymptote was where? That was when x equals 0, which is where this function is undefined. So that will always be the case that a rational function has the vertical asymptote where the function is undefined. And so that should make sense to us, right? Because the vertical asymptote is telling us that the function can never have that value for x, and it can't ever have that value for x wherever it makes the function undefined. So that's it. That's the end of video 1. Come on back and we'll look at the second video for section 3.7.